Hi everyone, this is going to be a video walkthrough of problem 2 on the exam prep worksheet for shortest paths and MSTs, and this problem is called conceptual shortest paths. And the prompt states, answer the following questions regarding shortest path algorithms for a weighted undirected graph. If the statement is true, provide an explanation. If the statement is false, provide a counterexample. Part A, if all edge weights are equal and positive, the breadth first search starting from a node A will return the shortest path from a node A to a target node B. So what this is saying is that if we ever have some sort of graph, let me just quickly create a graph. Let's say we have A and B, okay? Oh, you guys may not be able to see that. Let's move that down. Okay, so say we have some graph with A and B, and then we run BFS. So let's say that this path is the path between A and B with the minimum number of edges. My claim is that BFS, let me write this down. BFS will always find the path between A and B. Let's move this graph down. With minimum number of edges. Okay, so in this example, if this path between A and B is with the minimum number of edges, BFS will find that path. Okay, and the reason BFS does this is that BFS searches by edge. That's not a really great way of explaining it, so let me kind of draw out an example. Let's say that we kind of have this graph. Okay, so how BFS works is that we're first going to look at all of the people that are one edge away. Okay, then what we're going to do is look at all of the people that are 2 edges away. Okay, then we're going to look at all the people that are 3 edges away. Then we're going to look at all the people, oh gosh, all the people that are 4 edges away, right? And what we can see here is that if this path between A and B is the path with the minimum number of edges, we know BFS will find this path before it finds a path with more edges, right? Before it finds this path, say. Okay, so now that we understand that this is true, how does this help us solve the problem of figuring out whether this is true or false? Okay, so since BFS will always find the path between A and B with the minimum number of edges, what we can realize is that if all of the edges are of the same weight and they're all positive, then the path with minimum number of edges is the shortest path, right? And how we can see that is if we have a path with 4 edges, and all of the edges are of the same weight, right? They're all equal and positive. And then we have another path with 5 edges. We know that this path will always be of weight that is less than this path, right? So that is all for the first problem. And we can quickly condense this as our explanation. It's a little too small, but doesn't hurt for the future. So this is true. And then the explanation is over here. Okay. So let's move on to the next part now. The next part states, if all edges have distinct weights, the shortest path between any 2 vertices is unique. So this problem is actually pretty tricky. And how I would approach this on an exam is, let's assume this is false. Let's try to think of a counterexample. If we fail, we say it's true, right? So let's try finding a counterexample. I think finding a counterexample is sometimes easier than proving something is true, right? So if we had a counterexample, it means that there's two ways of going from A to B. Let's say we have a top path, and let's say we also have a bottom path. And we want to show that even if the graph has unique edges, it's possible for the total weight of the top path to be equal to the total weight of the bottom path, right? That's what we're trying to create this counterexample for. Okay, so let's say that on this top path, it was composed of two edges. And let's also say that for the bottom path. Okay, now let me just like randomly assign the edges of the top path and see if I can somehow make the bottom path of the same weight. So let's say that this is 4 and 5. What we can see here is that I can set this to be 6 and 3, and there's two paths between A and B, both of the same weight, but all of the edges are distinct, right? So we can see here is that we fulfill this property, all the edges have distinct weights, but we found two paths of the same cost. And if this was the entirety of a graph, we see that these two paths of equal cost are the shortest path, right? So we can say this is false. And then we can just pull up this counterexample. Cool. So moving on to the next one. This one's also a bit tricky. Adding a constant positive integer k to all edge weights will not affect any shortest path between two vertices, right? So let's look at an example of a graph. Let's say we have some graph between A and B. And let's say it's composed of a top path, and let's say it also has a bottom path. Let's just say the bottom path only has one edge. Okay. So we have a top and bottom path. Okay. And let's say that this top path is the shortest path. So let's say this is the shortest path. Okay. So my idea here, the intuition for the counterexample I'm going to create is that if we add a constant positive integer k to all edge weights, what this will do is this will favor paths with less edges. So why will this happen? Why will paths with less edges be favored if we add a constant positive integer k? The reason for this is that looking at this top path, which has more edges, if I add k to each of these edges, and I also add k to the bottom path, we see the top path goes up. The total weight of the top path goes up by 4k, whereas the total weight of the bottom path only goes up by k, right? So we can see here that if this top path used to be the shortest path, after adding k to each edge, this top path could potentially increase in weight that is so much compared to the bottom path that the bottom path now becomes the shortest path, right? That's my idea. So let's put some edge weights here and actually see a good example of what I'm explaining. So let's say that we have this example. So we can see here that this indeed is the shortest path, right? But if I add, let's say that k is equal to 1, if I add 1 to each of these, what we will realize is that each of these will go up by 1. The bottom one will change to 6, and then now this will become the shortest path, right? Okay, so this is false, and the counterexample is seen below. Okay. C. Okay, so let's move on to part F. Multiplying a constant positive or integer k to all edge weights will not affect any shortest path between two vertices. So what this is saying is that if we have some graph, I'm just going to use the same example here. Let's say that it's also split into a top path and a bottom path. This claim is that if we multiply all of the edges by some constant positive integer k, the shortest path stays the same. Okay, so let's kind of look at some example of that. Let's say the top path is composed of some edges. Let's say it has edge 1, edge 2, and edge 3. Okay, let's say these are the edges that compose the top path. And let's say the bottom path is composed of edges E4, E5, and E6. Okay, so what we can say is that the weight of the top path is E1 plus E2 plus E3. The weight of the bottom path is E4 plus E5 plus E6, right? And what I'm really saying here is that let's just say this is E1, E2, E3, and this is like E4, E5, E6, right? That's like this example, okay? Now let's multiply all of these edges by k, okay? What we can see here is that if we multiply all of these these edges by k, let's just say k is like 2, okay? What we can say is that this becomes 2 times E1, 2 times E2, 2 times E3, 2 times E4, 2 times E5, 2 times E6. So now our total weight, this is after modified, okay? So for the top path, our total weight will be 2 times E2 plus 2 times, or 2 times E1 plus 2 times E2 plus 2 times E3. In a similar light, what we can say is our bottom path will become 2 times E4 plus 2 times E5 plus 2 times E6, okay? So now let's just say, suppose without, I don't know, any loss of generality that this path is the shortest path, okay? Let's just assume that the top path is the shortest path. That means that this must be less than that, right? So if the top path is the shortest path, what we can say is that E1 plus E2 plus E3 is less than E4 plus E5 plus E6. So now, if we multiply all of these integers, or all of the numbers by 2, or any k for that matter, what we can see now is that this inequality still holds. The reason it holds is we can factor out the 2, and let's just replace this with k just to be even more generic. What we can say is that since this is less than that, right? And since these k's are both positive, we know that this left-hand side must be less than this right-hand side, okay? And what we can finally say is that this is indeed true. And my explanation was kind of given below, okay? So that is all for this video walkthrough. I hope you guys found it helpful, and I will charge my iPad. All right, see you all.